Okay, so I had originally planned today's talk to be on a slightly different topic, which is called random graphs. But since both my talks got preponed and rescheduled and everything, I will talk on a continuation of yesterday's topic, and as well as it has something to, it's closely connected to random graphs as well. So you can take the talk's title to be right. So what are random graphs? Anyone seen random graphs before? Anyone worked with? Okay. Have you guys done a course on graph theory? Anyone? Okay. But you have no idea of random graphs, right? Okay. So the thing is, maybe you all forgot or didn't notice yesterday. We did do some random graphs. So if you remember, we talked about a graph whose vertex set is the first n integers, and there is an edge between any I and j, the unordered pair I and j, with probability half for every pair I and j, right? This is really an example of random graphs. So what you will have is some kind of graph, not a particular graph, but a distribution over the set of all n vertex graphs. Okay, so then what do we mean by a random graph? It is a sequence of probability distributions, and there is one distribution for each value of n. Okay, so if you let Gn be the set of all n vertex graphs, then corresponding to every Gn, you have a probability distribution over the set, over this set, and you consider the sequence of distributions from, right? So what kind of distribution are we looking at when we talk about this graph with probability half, where every edge exists with probability half? Okay, I mean, it's the uniform distribution. We kind of talked about it yesterday. Because every graph, so whether the edge exists or it doesn't exist, the probability corresponding to the edge is the same. So what is the probability that any given graph comes out? When you draw this random graph, what is the probability that any fixed graph comes out? It's the same for every graph, right? This is the probability that any fixed graph will appear in your random graph. Okay, so if you recollect and make the connection between what we did yesterday and what I'm talking about right now, you will see that the random graph G n comma half is what we talked about yesterday, right? And it gave us, what did it give us? It gave us a lower bound on the Ramsey number Rk comma k. Okay. And that's like one of the uses. It's an example of why random graphs are useful. Okay. So to generalize from this, what you can get using random graphs is, so this kind of result where you wish to prove some existential property. Okay, you want to say something like there exists a graph which satisfies so many good properties, and you show that by showing that there is a random graph which satisfies your properties that you want. Okay, so that's one of the uses. Also, there are lots of other connections with subjects like statistical mechanics, for example. So the connection with statistical mechanics is you study kinetic theory of gases or something. So gases are very much like random particles. Okay, so they are like randomly moving about. You study something like Brownian motion. So all these are related to random structures. Okay, so in general, you have random structures, and graphs are a particular kind of structures. Right. So you have random graphs, random partially ordered sets, random directed graphs, random hypergraphs. Okay. So yeah. So what could be the uses? Just to summarize, there are many other uses. So one of the uses is it gives intuition. Okay, this one. Okay, this. Okay, I'm getting my order wrong. So this is one more use on deterministic graphs. It gives an idea of what general graphs look like. Okay, in so much as if you can show that most random graphs, okay, satisfy some certain properties, or they look, they have a certain structure, then it could be possible that you can prove it for all graphs. On the other hand, if most graphs do not have that structure, if most, and by most graphs, what I mean is random graphs with high probability. So what does it mean if a random graph has a certain property with certain probability? What would it mean for the set of all graphs? See, if a random graph G, you take, so this is a random graph, and this is your, you are drawing from this probability distribution. Okay, if it, you say that if the property, this is the property P. Now if G satisfies P with probability greater than, let's say, 1 minus 1 by 2 power n, then what would it imply for the number of graphs here? How did I do that? In Gn, which actually satisfy this property. So the question is, how many graphs in Gn satisfy this property? From this statement, what can you get? It's just multiplying, right? You just so right, I want the number of graphs in Gn such that so what you will get is this is at least say every graph appears with some probability, let's call it small p, okay, then it is simply okay, or let's say every graph appears with the probability pg, okay, then it's simply the summation over all graphs the probability pg, right. This is just you see where this is going. So if PGs are all equal, this summation will be just, okay, so let's say I take the uniform distribution, then what I will get is that the number of graphs is at least this much. And this is a huge number, right? Because this is like 2 power n square and this is 2 power just n. So this is negligible compared to, it's negligible compared to 1 anyway. So the point is that almost all graphs you can see satisfy the property P if I were to take the uniform distribution. But I didn't take the uniform distribution, I took a more general case where every graph appears with some probability which depends on the graph, then you will get this kind of a notation. But you can see that the number of graphs which satisfy the property P is related to the property that a random to the probability that a random graph has of satisfying the property P. So what it says is that if a random graph satisfies a certain property with very high, yeah.
How do you get this 1 minus 1 by 2 pi and what is that?
No, this is just an example. It's an example. So what I'm trying to say is that if this number is very close to 1, like this one is, see this one tends to 1 as n tends to infinity. So the point is that if a random graph satisfies this property with very high probability, then you can say that most graphs will satisfy the property with, most graphs will exactly satisfy the property. And then there you don't think about probability. So it gives some intuition on deterministic graphs, okay. Moreover, if you can show that there exists random graphs, okay, so even with some small probability, if you can show that there exists random graphs which satisfy certain other properties, then you can be sure that a statement that the negation of that statement cannot be true for all graphs, okay. So this was one example where I showed that most graphs satisfy something. On the other hand, if you can show something like the probability that G satisfies P is at least some epsilon, where epsilon is a constant, then it would mean, like I talked about yesterday, it would mean that the negation of P, okay, is not true for all graphs. Okay. So again it gives some intuition. So both these examples are how you of how you can get intuition on deterministic graphs, and by deterministic graphs I mean like fixed graphs using random graphs. Okay. Okay, that's one thing. Then there are connections with statistical mechanics and actually with several other fields. Okay, maybe I should have made that one. Connections with what else? So there are deep connections with theoretical computer science. Maybe I'll talk about those a little bit more now. Okay, so what are the connections with theoretical computer science? So you guys are familiar with NP completeness, NP hardness? You are. Okay, so most people are not. So what is NP completeness? Maybe actually you will hear more about it in later lectures by other people, but maybe I should give. Okay, it's you take some problem on graphs. Okay, you have some real life problem in computer science, and you can model it as a problem on graphs, right? Say traveling salesman. How many of you guys know the traveling salesman problem? Okay. Okay, the same guys who know NP completeness, of course. So, okay, maybe it's better I just talk about graphs rather than go into NP completeness and those things. But you can take my word for it that there are many problems whose many algorithmic problems where it's very difficult to or very unlikely that a polynomial time algorithm will exist. Okay, so what I mean by that is, let's say you have some problem on a graph, like let's say you want to find the size of the maximum clique. So a clique is a subset of vertices where all edges are joined. Okay, so this is like some clique C in the graph G, and of course, so you are trying to come up with an algorithm which will find the maximum sized clique, okay, or a maximum sized clique. Now, of course, this algorithm will take time which is proportional to the size of the graph. So if the graph is given in terms of its edges, then the input size is order of n square, right? The size of the graph is the number of its edges, which is something like n square, okay, right? Because it's n choose 2 at maximum. Now, so what you want is an algorithm which will take some time, which is f of n square, let's say, okay. But what you would like is that this time should be polynomial in n, or polynomial in n square, okay? Polynomial in the size of the input. So such algorithms are called polytime algorithms, okay, polynomial time algorithms. So right. Now, why is that? It's because so why is this? It's because suppose you take some time which is like 2 power n, okay, and you take some time which is n power, let's say 100. Now, if you take n to be some value like let's say 30, okay, or any slightly large value, what you will get is that this number is much larger than this number. I mean, it grows extremely fast. See, if you increase n by 1, this number doubles, whereas this number only grows by a fraction, okay. So and not even a constant fraction. So the point is that these functions, all of these functions, now even if I have 1.001, even such functions grow much faster than these functions. Okay. So that's why what you would like is that this function f of n square or whatever, it should be bounded, okay, it should be O of, so it should be bounded by a constant time n to the c, where c is some other constant. Okay, so it's like, so I'm saying what I mean is it's less than some c prime times n to the c, where c and c prime are constants. Okay, so that's what you would like in any algorithm, any graph algorithm or any general algorithm. You would like the size of the time of the algorithm to be polynomial in the size of the input. Okay. Now the problem is with a huge number of problems, like there are thousands of problems on graphs or in general, where it's highly unlikely that you would ever find such an algorithm. Okay, because they are all, so what has been shown is that they are all connected in the sense that there are many such problems. Let's call them P1 to whatever, P10,000 or whatever. All these problems are such that if you could solve any one of them, if you could find a polynomial time algorithm for any one of them, you would find polynomial time algorithms for all of these. But nobody has, and people have tried on different problems for like 30, 40 or more years, and nobody has so far found polynomial algorithms for all of these problems. Okay, so these problems are so the decision, there's a decision version and there's an optimization version. Okay, so right, these differences are like a bit finer differences, but what I want to say that these problems, you call them either NP complete or NP hard. So what does NP complete or NP hard mean? It means that given a problem instance, okay, you have a certificate which is of polynomial size. So why do I go for a certificate? It's, yeah, you have, so what is the problem instance? In this case, in the clique example, let's call the problem clique. Okay, so what is your input? Your input is two things. It's G, the graph, and it's a number k. And the question is, does G have a clique of size k? Okay, so this kind of problem is known as a decision problem, where you need to decide whether the answer is yes or no. Okay, and okay, so right, why is this problem in NP? It's because suppose you take a set of k vertices and you show that you print the edges of those k vertices, right? Then you can easily check that all those k vertices are present in the graph. So there is a certificate which is of very small size. In fact, its size of order k square, which will show that G has a clique. Okay. On the other hand, of size k. On the other hand, if G doesn't have a clique of size k, then there is no such certificate. Then may or may not be. Okay. The requirement for a problem in being in NP is that there should, for the yes instances, if the answer is yes, there should be such a certificate which is of polynomial size. Okay. So these problems are in NP, and what I was saying previously was that you show that all of these problems are kind of reducible to each other, as in if you could solve any one of them, you could solve any other one of them. Okay. So of course it's all that you need to show is one kind of reduction to, and then you show that these reductions are like they are transitive, okay, because they are all polynomial. Anyway, I'm going into too many details. So yeah, something like you just need to reduce this to this, and suppose you reduce P2 to P3, then P1 you can reduce to P3. So what it means is, if you could solve P3, you could also solve P1, right? And let's say you have some connection like this. So that's NP completeness. So there are many such problems whose decision versions. So typically, so the thing is that decision versions you call NP complete, and optimization versions you call NP hard. So what this means is, the optimization version, you are just given a graph and you want to find the maximum sized click, okay. So you are not given the number k. That's the difference. So the optimization is what you really need in practical purposes, of course, right? Unless you are a complexity theorist, you would generally need the optimization version. And right. So what do random graphs have to do with such problems? What random graphs can do is, they can show. Okay, so before that I need to go into approximation algorithms. So what are approximation algorithms? I have this problem, say click, and let's take the optimization version now, okay? Or let's persist with the, anyway, decision. Right. Or no. Okay, so I want to find the size of the maximum sized click inside G, but I know that it's unlikely that I could ever, find the maximum sized click in polynomial time, right? But can I do an approximation, as in, okay, can I go for kind of next best solution, okay? So that approach is what is called approximation algorithms. So the idea is, maybe I can't find the maximum sized click, but can I find a click whose size is at least half the maximum? That's the idea. Or at least 1/3 or 1/10, okay, or maximum divide by log n. So the point is, you have the maximum size, which is the optimum size, let's call it opt, and you have a ratio. So suppose this is a maximization problem. So I want to find the maximum size of the click. Then can I find, okay, where alpha is, yeah, right. So can I find a click of at least this much size, where alpha is some number or some function of n? Can I find a click of this size? Okay, such in polynomial time. So such an algorithm would be an approximation algorithm, which would give an alpha factor approximation, okay, for maximization. For minimization, you multiply it by alpha. So alpha is always greater than 1. Yeah. So if you are looking for some kind of minimum thing, then you say that the size is at least alpha times the minimum. That's what you are looking for. So this approach is known as approximation algorithm. And there are many problems which are NP hard, but which have good approximation algorithms. So you can find a 2-factor approximation algorithm, or even a 1 plus epsilon factor approximation. Okay, but there are many other problems which don't have good approximation algorithms. So click is like one of these problems. So what it says is, if you have a click, so I mean what says, the thing that I'm talking about is the hardness of approximation. So it turns out that this clique problem is not only hard to compute, it's also hard to approximate, and it's extremely hard to approximate. Okay, it's not only NP hard, but right, it's, so this is a theorem which says that basically is in wait, I shouldn't state it like that. Okay. Right. So that's the thing. So unless p equal to np, you won't even have an n to the 1 minus epsilon. In fact, there are even better results than this, which say that you can't even have 1 minus some small o of 1. So suppose I give you a graph and I tell you it has a clique of size n by 2, right? And what this would mean is you couldn't even find a clique of size n by, so you know that there is a clique of size n by 2, and I am telling you to find a clique of this much size, and even that could be NP hard. Okay, so not n by 2, maybe n by some constant. So you know that there is a clique of linear size in n, but I only want you to find a clique of this much size, and even that would be very hard. Okay. So this is kind of what this theorem implies. So you see that the clique problem is not only hard to compute, but also hard to approximate. So, and that's where random graphs come in. Okay. So finally I can talk about random graphs. Yeah. So right. The other theorem would be there exists a two-factor So you couldn't get n to the 1 minus epsilon, but you can get a two-factor in random graphs. So what does that mean? It means that although the worst case difficulty is very high, but the average case, so yeah, I rub those things, but yeah, this, why do you get the intuition? So one point was that by random graphs, I mean most graphs. In some sense, in some probabilistic sense, I mean most graphs, right? So what it means is that most graphs, the clique problem is easy to approximate. Okay, you get a two-factor approximation, although you don't get anything better than 2. So 2 plus epsilon may be very hard to get. Sorry, 2 minus epsilon may be very hard to get, but at least 2, that's a whole lot better than n to the 1 minus epsilon. Okay. So there are connections with theoretical computer science, and I think I gave 2 of those connections at least. Right. There are many other connections. So this was like algorithmic results. Also, besides this, you can do something like you can come up with even problems where you do have polynomial time algorithms. You can come up with faster polynomial time algorithms on random graphs. Okay, so right. There are some other connections with computational complexity, and I won't be going into those. Right. And of course, there's connections with, I mean, it is a part of combinatorics, so it will have connections with many subfields of combinatorics. There's connections with number theory. So especially additive combinatorics. So additive combinatorics is actually number theory. It's not just combinatorics, right? And discrete geometry. So there are connections with everything in discrete math. Okay, somewhere or the other you will come up with connections. So yeah, so much about the uses of random graphs. Okay, so yeah, this lecture is going to be more about uses, and I don't know, maybe one or two properties I'll be able to show you. Right. So I have talked a lot about random graphs, but other than this small example of GA n comma half, I have not described much about random graph models. So how do you begin to analyze random graphs? Of course, it's a probability distribution on the set of all graphs and so on and so forth, but what kind of probability distributions are you looking at? So there are different models of random graphs. Okay. Right. So the first model is, so I'll go in like chronological order really. So the first model is GNM, and this is really the first model that was studied specifically under random graphs, and so this study was initiated by some path-breaking papers of Erdős and Alfred Renyi in 59 to 61. So there were like several papers which really initialized the study of random graphs in a big way. Okay, and the model that they were primarily looking at is this GNM. So what do you have here is you have n vertices and you have m edges. Okay, and you look at all the graphs which have these two properties, and you take a uniform distribution on those graphs. Okay, so it's not anymore a uniform distribution on the set of all n vertex graphs. It's all n vertex m edge graphs. Okay, right. So how many graphs do you have which have n vertices and m edges? Any idea? Yeah, that's right. N choose 2, choose n m. So you have n choose 2 edges and you choose any m edges, right? But then, right. So when you take a uniform distribution, what it means is that every graph has this much probability of appearing. So this is the probability that you take any fixed graph which has n vertices and m edges, and then G belongs to G and M will be this, right. So this is kind of a little hard to analyze, but it's very closely related to the next model that I will talk about, which is the most extensively studied model, I would say. Erdős and Rényi had also talked a little about this model, and what they showed is that these two models are very close to each other, and this is really the model that we talked about yesterday. We used rather yesterday. We had p equal to half, but in general it's some G n p where you will have n vertices. Okay, you have you don't have m edges. What you have is that the probability that this set ij is an edge is equal to p, okay, for every I and j. For choose any two vertices I and j which are not the same, and the probability that ij is an edge is p. Okay. Now this p can be a constant, or it could even be a function of n. So p could be something like 1 by n or 1 by root n, okay, or it could be a constant, but in any case, now what is the probability that a fixed graph, again I mean just to give some starting point on how to think about these objects. So you take a fixed graph G, again what is the probability that G right. So what is the probability that this G appears? Any idea? So by this notation what I mean is, see this is a distribution, so anyway what is the probability of this G in this distribution? It has n vertices, let's say, okay, of course otherwise doesn't make sense. So any idea? If you can assume that G has some n, of course n vertices it will have, you can also assume it has a fixed number of edges, let's say m edges. So it's not that hard. So anyway, should I, okay, maybe I should give you some more time. Okay, so let's take a small example and see. Why do I draw these circles? Right. Let's take n to be 4, okay. Now I say that so these are my vertices. Now I say that every edge appears with probability p. Now this is my graph. What is the probability that this graph appears? You understand what I'm doing? Like there are 4 vertices, you choose any pair of vertices, the probability that the edge appears is p. Now I give you this graph, what is the probability that this appears? This is what is the probability that this is exactly the graph which you come up with? It's just this, right? Right. So this 2 is 6 minus 4, right? 6 minus 4, right? So the idea is that these 4 edges are exactly the ones which appear, and these 2 edges are exactly the ones which don't appear. Okay. So this probability, what is that? It's exactly these m edges will appear and these other edges will not appear. Okay. So it's again a product space and everything. So then what there's a nice thing about this model. The nice thing is that in some sense it's a binomial model. Okay. So what is the probability that the graph which appears has exactly m edges? N choose m, n choose 2 choose m times right. So what is the probability that G appears in this such that E of G so how many, so that will be exactly the number of graphs which have m edges times the probability. So notice that every graph which has m edges has exactly the same probability. So in that sense it's again uniform over all graphs which have m edges. So when you condition it on the fact that, if you condition it on the fact that G has exactly m edges, you will get back the previous distribution. Okay. Right, and this is exactly n choose 2 choose m times p to the m right. So that's one of the nice things that you get with this model, and because of this model is quite hard to this model is quite easy to analyze. Okay, so yeah, there is one more model which I would have liked to talk about, and okay, so there are many models and maybe you can come up with your own model for your own problem, whatever, but so this model is also known as the it's not only the GNP model but also the binomial model, because you see that p and 1 minus p are following a binomial distribution with, so this is really the distribution is you have n choose 2 comma p, p of n choose 2 comma p, this is the distribution. You see, you have a coin with bias p, you toss it n choose 2 times, and based on that you get your graph. Based on the results of these n choose 2 tosses you get your graph. So what is the distribution of this this experiment? It's exactly binomial n choose 2 comma p, right. So there is one more model which is, okay, so you can try this next problem in your free time, maybe G n comma d, and this is the uniform distribution over all n vertex deregular graphs. Okay, so can somebody tell me how many n vertex deregular graphs are there? Seems like a simple problem, right? You have n vertices, every vertex has d edges. So how many such graphs can you have? Okay, this is not so easy. Okay, it was found only in the 20th century. So and graphs have been studied since Euler's time, so it's not such an easy problem. So even don't even know how many uniform, how many n vertex deregular graphs you have. How can you come up with a model for such graphs? So it's not so trivial. So this model is what is known as the configurations model. So the thing is, this problem was initially solved in maybe 1968 or something. Right. So maybe I should tell you a little bit about the history. This problem was open for a long time. Okay. The problem is number of graphs number of deregular graphs, and in I think late 50s or late 60s, a person called Reed, or is it Robinson? Reed, okay, first got the result. He computed this number, maybe late 50s or 60s, okay, and then they were, but the formula was quite complicated. So the way he got it is he used Polya's theory of counting, but the formula itself is quite complicated, and in these problems often the asymptotics are more useful than the exact formula. But the formula was so complicated that it was not even easy to see the asymptotics from the formula itself. So what these two people did was they got a different proof of this problem, and they also gave the asymptotics of the problem of the number, okay. And finally in late 70s, Bela Bolubash, he came up with this model, the configuration model, which gives the asymptotics very nicely. And the nice thing about this is that you can use it to get a uniform distribution over all such graphs, and you can also study random deregular graphs from these things, okay. So it's comparatively easier to study, although not as easy as this. And what is this model? So the idea is, see, why do you have a problem when you start this counting? The problem is, you take a vertex, you have some d edges, right? But and you can do this for every vertex. For every vertex, you can choose d neighbors, right? But then these things are not independent, right? Because the neighbors, for the first vertex you can do it, but for the other vertices, you have to know whether the previous vertex, how many neighbors it already has from the previous vertices, right? You see my point? Suppose these are my vertices. Now I choose some d neighbors. Okay. This one I can again choose some d neighbors. Let's say I choose this. So I choose 3 neighbors for each one. But for this one, I have already chosen this. So only thing I can choose now is 2 neighbors, right? And for this one I have chosen 2 already, so I only have to choose 1 neighbor. So so it's no more uniform. These probabilities are not uniform anymore, you see. So they are not only not independent, this non-independence induces non-uniformness. So the way these people deal with this is they break every edge into 2, okay? And right, so what you will have is you will have what are called half edges, okay? So okay, so how many edges do you have in total? Can you see that? You have a d-regular graph. How many edges do you have? Yeah, nd by 2. Okay, so how many half edges do you have? It's nd. So you have nd half edges. You split them in groups of d. Okay, so you think of a set 1, 2, nd. You think of this set. You choose any random permutation that you like, okay, right, and then you split them into groups of d. You split this random permutation into groups of d, okay, and yeah, so it's like you have d groups. So there are d elements. So you will have n such groups, right? And then what you do is you take pairings. Okay, so let me talk about it once again. So I have elements like this. I have 1 to d, then d plus 1 to 2d, and so on, right? I say that these will be the half edges corresponding to the vertex 1, d plus 1 to 2d corresponds to the vertex 2, and so on. Okay. So this is what I meant. Okay, so this is before you take the random permutation. You say that this corresponds to vertex 1, this corresponds to vertex 2, and this corresponds to vertex n. Okay. Now you take a random permutation. So this is the first step. This is randomly permute them. And the third step is take pairs. Okay. So suppose your permutation is something like this: 1 d plus 1 2d whatever. Okay. So you can take pairs like this. So 2 each, right? And how many ways can you do this? So clearly you permute nd things in nd factorial ways, and now how many ways do you take the pairs? See, these permutations since you are only concerned with these pairs, okay, this is equivalent to this, right, instead of, so all these pairs are equivalent. So all such permutations which you get by twisting these pairs or by twisting the order of these. So this, for example, let us say this is some 5d plus 3, okay. This is equivalent to d plus 1 comma 1 comma 2d comma 5d plus 3, but it is also equivalent to 5d comma 3 2d d plus 1 1. Why? Because this was one edge. So these pairs are really our edges, right. This was one pair, I took this pair to this part, I took this pair to this part, and then I changed the orders, and it's still the same, right. So then how many ways can I do this in, right. And for each such rotation I can further rotate these things, right. So notice that I am only rotating the pairs, I am not changing the order within the pairs, okay. So I can still change the order within a pair, and that would give me, you know, further equivalent. So how many can I do in this way? I have so many pairs, sorry, I have nd by 2 pairs, each of them I can rotate in 2 ways, so it is 2 to the nd by 2. So this is the number of ways in which I can take pairs, okay. So this is just a counting thing which you would need if you wanted to work with this model. Should rub these things. Okay, and that's it. So you have nd half edges, you have got nd by 2 edges, and that's it, you took pairs. Is there any problem with this now?
Trivial graphs, like there are n vertices, each of them having d self-loops to each other.
Sorry?
With each of them having d self-loops.
Yes, d by 2,
Yeah, d by 2.
or
D will be d.
Yes.
Or there can be 2 vertices where there can be d multi-edges from one to another.
exactly. You got the point, right? So you could have multiple edges, or you could also have self loops. So that's the remaining problem. So what you do is you condition on not having any multiple edges or self loops. So I can say they are all cycles of size 1 or 2, right. That's really what I wanted. There should be no multiple edges, and there should be no self loops. So the cycles, the minimum cycle should be of size 3, right. And if you condition on this, then you will get what you wanted, a uniform distribution over all n vertex deregular graph, because notice that each graph again occurs with equal probability in this model. So what is the once you do this, what is the probability with which any graph appears? So that is related to this problem, and I will leave you to figure it out. You see, you fix a graph, and now you try to think of in how many ways that graph could come up in this model exactly. So once you do that, you will find that the number of ways is independent of the graph, which means that every graph will appear an equal number of times, which means when you condition it on the graph being what is called a simple graph, then okay, sorry, not the number is not same for every graph, the number is same for every simple graph. Okay. So when you condition it on the graph being simple, you will get that the distribution over simple graphs is uniform. Okay. But this is not, I mean, it's not that you just say that condition and you're done. You need to actually show a certain thing, which is when you condition, what is the probability with which you will not have any cycles of size 1 or 2. You need to show that those probabilities are bounded by a constant. Okay. And what you can show is that the probability with which a simple graph appears is something like, okay, it's a slightly involved expression, but the main point is that the expression depends only on d. It does not depend on n, which means, so here typically we take d to be a constant and n to be going to infinity. So the probability that g belongs to g, sorry, gn comma d is simple, this is something like e to the minus d minus 1 square by 4 or something like that. Okay, I don't remember the exact expression because, but there is nothing, it has nothing to do with n, which means that right, which means that when you condition a graph, you take a random graph, a random configuration. So these things are called configurations now. You take a random configuration, and when you condition it on not having any cycles of size 1 or 2, that will amount to multiplying it with this probability, because see, probability, you, let's say A is the event that you took a random configuration, and B, yeah, so now you are conditioning it, right? Sorry, not, this is not the conditioning, sorry. What you want is this. You want a random configuration which also has the property that there are no cycles of size 1 or 2. Okay. And what is that? This is the probability of A conditioned on B times the probability of B, right? So this is the probability that you get a random d-regular graph. And this is the probability that this graph is simple. Okay. So, right. So now you can see that with, at least with constant probability, which is this, you will get a, so the idea is with constant probability, you get a random, and by random I mean uniformly random, n vertex d-regular graph. Okay, so this was one more model. So okay, so I think I spent all my time in just dealing with uses, definitions and models, and I think I have given some kind of an overview of what random graphs are. I don't think there is any time for examples, but maybe I can do just one. Okay, one example is the example that we did yesterday. Okay, you have J n comma half, the RKK example. You had a G n comma half, and what was the probability that it did not have any clique or independent set of size k for some k, right? And the way we did it was we took the expected number of such independent sets. So we looked at this number, right, n choose k, and I described it in terms of union bound, but I can also say that this is really the expected number of cliques or independent sets of size k. And when this expected number is much less than 1, then you can say that most graphs will not have this property, will not have any clique or. So this implies most, in some sense, okay, graphs, and by which I mean again most graphs or random graphs will not have copy of for that k, for this value of k, right. So maybe a few things I should still, yeah, I think I can take maybe 2 or 3 minutes extra, and I have 2 or 3 minutes, so I get 5 minutes, and I can say something in 5 minutes. Yeah, so okay, so there are certain how should I say, there are certain phenomena with regard to random graphs, okay, and so these phenomena can be described by using certain statements in probability, which we say something like this. It means with high probability or asymptotically almost surely. Okay. I mean, this thing you just need to read the you'll just need this in order to understand the literature. Asymptotically almost surely. Okay. So what does this mean? Both these statements mean the same thing. It means that the probability that some event occurs, so I say that E occurs AAS. What does that mean? Means that E occurs is tends to 1 as n tends to infinity. So where is n coming from? N is this n. So any event is an event on an n vertex graph, right? So that's where this n comes from. So naturally the event will depend on n. The probability will depend on n. Now what it means is that the probability to say that this is asymptotically almost surely is that this will tend to 1 as n tends to infinity, right? And similarly, if I say that it does not occur almost surely, means that the probability goes to 0 as n tends to infinity, right? Right. So this you could take it as a problem very simple to this. the question is, what is AAS, the size of the largest click on G n comma p. Let us say p is fixed. So, p is some fixed real number, right. P is a fixed real number. Now, what is AA asymptotically almost surely the size of the largest click, and I think based on what I have done so far, you can find the upper bound at least. So, what you need to show is that some k, okay, you need to show two things, that AAS, there is no click okay, no click of size k plus 1, and secondly you would need to show that AAS, this KK exists in GNP. Okay, so these would be the two parts, but suppose I do not ask you to do this one, just try to do this one, and this is the same as, essentially it is the same as what we did yesterday. Okay. Only thing is, we were trying not to have any clique or independent set. Here we are just trying not to have any clique of size k plus 1. So, yeah. So, yeah, that is the thing. Okay, thank you.